For a 240/120 volts delta 3-phase system, phase A is identified as black. The high leg, which is phase B, is orange. Phase C is red. Now addressing the possibility of a 240/120 volts Y3-phase system, yes, it is possible to have such a configuration. In this 240/120 volts Y3-phase system, phase A is black, phase B is red, and phase C is blue. When dealing with electrical systems, proper phase identification is crucial for safety and correct operation. Using the wrong color code can lead to dangerous situations, equipment damage, and code violations. Let's delve deeper into each system to understand why these color codes are important. In a 240/120 volts delta system, the high leg, also known as the stinger leg or wild leg, is typically identified as orange. This high leg is 208 volts to neutral, unlike the other two phases, which are 120 volts to neutral. This voltage difference is why it's critical to clearly mark this phase. Connecting a 120 volts load to the high leg will result in damage to the load due to overvoltage. The NEC, or National Electrical Code, provides guidelines for color coding electrical systems. While the NEC does not mandate specific colors for all applications, it requires that the grounded conductor, usually the neutral, be identified by white or gray. The equipment grounding conductor must be green or green with yellow stripes. For ungrounded conductors, which are the phase conductors, the NEC allows for any color other than white, gray, or green. However, it is a common practice to use black, red, and blue for 208/120 volt systems, and brown, orange, and yellow for 480/277 volt systems. The 240/120 volts delta system with a high leg is often used in light industrial or commercial settings where there is a need for both 240 volts 3-phase power and 120 volts single-phase power. The 240 volts is used for equipment such as motors and HVAC systems, while the 120 volts is used for lighting and receptacle circuits. The high leg is derived from a center tap on one of the 240 volts windings in the transformer. This center tap creates two 120 volts legs and a 208 volts leg when measured to the neutral. Understanding the phase relationships in a 3-phase system is essential for troubleshooting and maintenance. The 3 phases are 120 degrees apart, which means that the voltage waveforms reach their peak at different times. This phase difference is what allows 3-phase motors to start and run smoothly. In a Y system, the 3 phases are connected in a Y configuration, with the neutral point at the center. The voltage from each phase to the neutral is the same, which is why 240/120 volts Y system is possible. In this system, each phase is 120 volts to neutral and 240 volts between phases. The 240/120 volts Y system is less common than the 208/120 volts Y system, but it can be used in certain applications where 240 volt single-phase power is needed in addition to 120 volts power. The color coding for 240/120 volts Y system is typically black, red, and blue for phases A, B, and C respectively. This is the same color coding as a 208/120 volts Y system. The neutral conductor in both systems is white or gray, and the equipment grounding conductor is green or green with yellow stripes. When working with electrical systems, it is important to always verify the voltage and phase identification before making any connections. Use a voltmeter to measure the voltage between phases and to neutral to ensure that you are connecting to the correct voltage. Use a phase sequence indicator to verify the phase rotation. Incorrect phase rotation can cause motors to run in reverse or not start at all. Always follow safe work practices when working with electricity. Wear appropriate personal protective equipment, such as safety glasses and insulated gloves. To energize the circuit before working on it whenever possible. If you must work on a live circuit, use insulated tools and take extra precautions to avoid contact with energized parts. If you are not qualified to work on electrical systems, hire a licensed electrician. Working with electricity can be dangerous, and it is important to have the proper training and experience to do the job safely. The NEC is updated every 3 years, so it is important to stay up to date on the latest requirements. The NEC is available for purchase from the National Fire Protection Association, or NFPA. Many states and local jurisdictions adopt the NEC as their electrical code. In addition to the NEC, there may be other local codes and regulations that apply to electrical installations. It is important to check with your local building department to determine what codes are in effect in your area. Proper grounding is essential for electrical safety. The equipment grounding conductor provides a path for fault current to flow back to the source, which helps to trip the circuit breaker and prevent electrical shock. The grounding electrode system provides a connection to earth, which helps to stabilize the voltage and provide a low impedance path for fault current. The grounding electrode system typically consists of a ground rod, a ground ring, or a metal underground water pipe. The size of the grounding conductor and grounding electrode system is determined by the size of the service entrance conductors. Bonding is the process of connecting all metal parts of the electrical system together to create a low impedance path for fault current. Bonding helps to prevent voltage differences between metal parts, which can cause electrical shock. Bonding is typically accomplished by using bonding jumpers to connect metal enclosures, raceways, and equipment together. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning or other events. SPD divert the surge current to ground, which helps to prevent damage to the equipment. SPD are typically installed at the service entrance and a branch panel boards. Arc flash is a dangerous electrical hazard that can occur when there is a short circuit in the air. The arc flash can produce intense heat and light, which can cause severe burns and other injuries. Arc flash protection is required by the NEC for certain electrical equipment. Arc flash protection typically consists of arc-rated clothing, gloves, and face shields. Electrical safety training is essential for anyone who works with electricity. Electrical safety training teaches workers how to identify electrical hazards and how to work safely around electricity. Electrical safety training is required by OSHA, or the Occupational Safety and Health Administration, for certain types of electrical work. In summary, understanding the color codes and configurations of 240/120 volts delta and Y three-phase systems is crucial for safe and effective electrical work. Always verify the voltage and phase identification before making any connections, and follow safe work practices to prevent electrical shock and other hazards. Stay up to date on the latest electrical codes and regulations, and seek professional help when needed. By following these guidelines, you can help ensure the safety of yourself and others when working with electricity. Furthermore, remember that the specific application and local codes might influence the best practices for color coding and system configuration. Consulting with a qualified electrician or electrical engineer is always recommended for complex or critical electrical installations. The information provided here serves as a general guide and should not be considered a substitute for professional advice. Remember to always prioritize safety and adhere to all applicable codes and regulations. The proper selection and installation of overcurrent protection devices, such as circuit breakers and fuses, are also critical for electrical safety. These devices are designed to interrupt the flow of current in the event of a short circuit or overload, which helps to prevent equipment damage and electrical fires. The size of the overcurrent protection device must be properly matched to the size of the conductors it is protecting. The NEC provides tables and guidelines for selecting the correct overcurrent protection device for various applications. Regular inspection and maintenance of electrical systems are also important for ensuring their continued safe and reliable operation. Inspection should be performed by qualified electricians or electrical inspectors. Maintenance should include checking for loose connections, damaged insulation, and other signs of wear and tear. Any problems that are found should be corrected promptly. Power quality is another important consideration for electrical systems. Power quality refers to the characteristics of the voltage and current waveforms. Poor power quality can cause equipment to malfunction or fail prematurely. Common power quality problems include voltage sags, voltage swells, harmonics, and transients. Power quality problems can be caused by a variety of factors, such as nonlinear loads, switching power supplies, and lightning strikes. There are various methods for improving power quality, such as installing harmonic filters, surge suppressors, and voltage regulators. Energy efficiency is also an important consideration for electrical systems. Energy-efficient electrical systems can save money on electricity bills and reduce greenhouse gas emissions. There are many ways to improve the energy efficiency of electrical systems, such as using energy-efficient lighting, motors, and appliances. It is also important to properly size electrical equipment to match the load requirements. Oversized equipment can waste energy and increase operating costs. Renewable energy sources, such as solar and wind power, are becoming increasingly popular as a way to reduce reliance on fossil fuels and lower electricity costs. Renewable energy sources can be used to supplement or replace traditional electricity sources. When installing renewable energy systems, it is important to follow all applicable codes and regulations. Smart grid technologies are also being developed to improve the efficiency and reliability of electrical systems. Smart grid technologies use sensors, communications, and control systems to optimize the flow of electricity. Smart grids can help to reduce energy consumption, improve power quality, and increase the resilience of the electrical grid. Electric vehicles, or EVs, are becoming increasingly popular as a way to reduce transportation costs and greenhouse gas emissions. EV require charging stations, which can be installed at homes, workplaces, and public locations. When installing EV charging stations, it is important to follow all applicable codes and regulations. The NEC provides specific requirements for EV charging station installations. As technology continues to advance, the field of electrical engineering is constantly evolving. New materials, devices, and systems are being developed all the time. It is important for electrical engineers to stay up to date on the latest developments in the field. There are many resources available for electrical engineers to stay informed, such as professional journals, conferences, and online training courses. The electrical industry is also facing a shortage of skilled workers. There is a growing demand for electricians, electrical engineers, and other electrical professionals. To address this shortage, many organizations are offering training and apprenticeship programs. These programs provide individuals with the skills and knowledge they need to succeed in the electrical industry. The electrical industry plays a vital role in our society. Electrical systems provide the power we need to light our homes, run our businesses, and operate our industries. By following safe work practices, staying up to date on the latest technologies, and investing in training and education, we can help ensure that electrical systems continue to provide safe, reliable, and efficient power for generations to come.